The subject today is invariants of singularities in zero and positive characteristics. And if you have any questions of administrative nature or something, Lynn is outside, and also myself. Let me remind everyone you should wear your badges. This is quite important for various reasons. And without further interruption, it's my pleasure to introduce Rob Lazarsfeld, who will talk about an introduction to singularities.
Well, thank you. So the idea of this workshop is that there are some invariants of singularities that have come up in the last few years. First in the analytic side of the field, but more recently they've turned out to have interesting and slightly mysterious connections with characteristic P geometry. So the theory was the plan was to sort of give talks explaining both the classical side and the more recent algebraic side of the story. So that's the kind of the goal of the mini school. And what I'm going to do is I'm just going to give a very hopefully elementary introduction to the complex analytic side of the story, or the algebraic side of the story, starting with just an introduction to singularities. So this is supposed to be quite elementary. Just what are the invariants? What's that people are going to be interested in? So let's start just in the with a single polynomial with complex coefficients. So we'll start with some polynomial, let's say f in n complex variables, or it's really going to be a local story. So we might take f to be a convergent power series, and we'll assume that it vanishes at the origin. So f of 0 is 0. Okay. And so what we're going to be interested in is we're going to be interested basically in the hypersurface defined by f. So d will be f equals 0 inside Cn. And you might imagine that you don't want f to have repeated factors, but that doesn't really make any difference. And so we're going to be interested in the local, geometry of D near the origin. So the question is, what does D look like? So we want to know local geometry of D near 0. So that's kind of the basic question. Well, there are two cases that happen. So the sort of simplest thing is it might happen that one of the partials of D is non-vanishing at the origin. And in that case, of course, D is a complex submanifold. So there's really nothing else to say. There is no local geometry. But if all the partials vanish, then that's that's where singularities arise. And so that's where we start today. So the definition is that 0 is a singular point. The origin is a singular point of D. And sometimes instead of writing D, I'll just refer to it by F, the defining equation. If what? So if all the partials of F vanish at the origin. And so this is where we get interesting local behavior. And so this is what we want to study. So let me, again, I apologize if I'm being too elementary. Let me draw the first pictures that everybody draws in this subject. So let's look at some singular points. So let's start with some plane curves. So we could take, for example, w, how do I want to do this? Okay, w squared minus z squared times z plus 1 equals 0. So what does this look like? Well, this is everybody's favorite nodal cubic curve. So this is D, and so here at the origin, we get some kind of double point. Now, notice that since we're actually happy to work analytically, this is locally analytically the same thing as just w squared minus z squared equals 0. So all this stuff is just fluff. So locally analytically, this is just z squared minus w squared minus z squared equals 0. So if we're really just working in the singularities, this is really we just have two little branches crossing at the origin. We could, for example, put in a third branch. Yeah, because you can take as a power series, you can take the square root of z plus 1. So then you get the difference of squares. Yeah. Or we could put in, let's see, do I need a new board here? We could just take this, we could just put in another branch. So we could take, let's see if I've got my equations right, z squared w minus, w cubed is 0. And then we get that's just the, well, it's just 3 lines.
Well, that's the question. If there were 4 branches, you wouldn't know what to guess.
Yeah, they're moduli. These things can have local moduli.
That's why I was worried.
Right. No, but this is just like that.
Well, you have 3, you're getting to the edge now.
Yeah, right. Exactly. They're not always linearizable like this, but just pictorially it looks like this. I should also say that I'm doing this thing that people always do, is I'm drawing pictures over the reals to. You're supposed to really imagine all of this taking place in C2, but as usual, I'm drawing R2 pictures. The next example, the last plane curve example, so this is the one I think that's going to be the star of the show today. So this is the first really interesting one. This is a cuspidal cubic. So here we get something that's a cusp. And then there are lots, once you get into 3 variables, into surfaces, you can get all sorts of, really, there are a lot of, people have made a lot of very interesting pictures on computers. Let me just draw the only surface example I can draw, which is a cone. So this is just z squared minus w squared minus u squared equals 0. Okay, so these are their simplest examples, but already for these double points of surfaces, you can get very, very elaborate behavior. But I'm certainly not going to draw it. Okay, so these are kind of the basic examples of singularities. Now, there's another construction that I'm not going to focus on too much, but it probably will come up in some of the other talks, and it's also important because it makes the connection between these ideas involving singularities and some questions in algebra. So there's a sort of another construction, or a variant. So instead of starting with a polynomial, you can start with an ideal in the polynomial ring or in the ring of convergent power series. So you take some ideal in the polynomial ring or in the ring of convergent power series, so an ideal. And then you can think of an ideal as actually giving you a series of polynomials that kind of, in some vague sense, are equisingular. So how does this go? So let's take generators for this ideal. So we'll say that the ideal is generated by a bunch of functions g1 through gr. And then what you can do is you can look at a general element of A, by which I mean a general C linear combination of those generators. So we'll say that a sort of a general element of A, of this ideal A, is something of the form F. So I just take a general linear combination of the generators of the ideal. So Ci, these are constants, and they're supposed to be general choices of the constants.
It's like generator, so.
Yeah, something like that.
Not a general element.
Well, people call it a general element because it's a general linear. The GIs are the generators. So I'm taking a general linear combination.
That's all products and things, right?
Yeah, right. But this is, yeah. So, this is what you mean by a general element. I mean, it's just we're just going to mean a C, because we want it to be a finite dimensional choice. So we're going to just take a C linear combination of the generators. That's all I'm saying. And so the idea is if you take this sort of general C linear combination of the generators, so for each of these things, each such choice, you get a polynomial. And in some vague sense that I'm not going to try to describe, all the corresponding hypersurfaces are somehow equisingular. So for example, if you take A to be just the square, or I guess I'm calling it ZW. If I take the square of this ideal ZW, then the general element, I get something that just has an ordinary double point like that. Or if I take A to be, for example, the ideal z cubed w squared, then I'm going to get something that, and some family of cusps. See, I would be looking at an equation like w squared equals constant times z cubed. So those are not in this case, they're kind of probably analytically isomorphic, but I get different hypersurfaces, but they all kind of look the same. And this is a kind of a useful construction because then, I mean, we're not going to really focus on it, but then the idea is you can use these ideas involving singularities to study the properties of this ideal. Somehow the singularities of these general elements somehow reflect the algebraic structure of the ideal.
Two general things are equivalent?
No, they're not going to be analytically equivalent.
In some weaker sense.
Yeah,
It looks the same.
yeah. For example, they have a simultaneous resolution of singularities. So that's one way of saying it.
You mean, does it depend on the choice of generators? Or?
What do you mean? Does it depend?
I mean, you can choose a different choice of generators for the ideal.
Yeah, I mean, I think if you once you fix, you want to be. I mean, once you fix a set of generators, then they're all going to look the same in some vague sense. But I mean, yeah, again, so, and if you take different generators, you would still have simultaneous resolutions for general things in this sense, because you.
This means a family resolution.
Yeah. So, but there's no. So, I don't want to spend too. There's one resolution that simultaneously desingularizes all these gadgets. Because you can talk about, I'm going to come to resolutions later. You can talk about resolving the ideal, which I'm not going to do, but one could do that. So in that sense, these are all coming in kind of smooth things in some simultaneous space living over these things. Okay. But I digress. So, okay, so these are kind of the most, these are kind of the most elementary singularities you can look at. And so what we want to do now is we'd like to look at what are the invariants of these singularities. So in particular, some numerical invariants. Okay, so what's the most naive numerical invariant? So let's do that first. Okay. Well, the most naive invariant of a singularity like this is just its multiplicity. So let me give the definition of that. So the multiplicity of such a hypersurface is 0. So given 0, so D, remember, is our f equals 0. But I'm also, as I say, I'm also often just going to talk about f. The multiplicity of D at 0 is just the order of vanishing, is just by definition the order of vanishing of f at 0. So, I mean, this is the most naive thing you can do. You take whatever equation f is defining f, and you just look what's the lowest degree term that appears there. Okay, so if we look at our examples here, the nodal cubic, the cuspidal cubic, and the cone, these are all double points. These have multiplicity 2. And, but the three lines have multiplicity 3. As you might think. Okay. So this is certainly the first invariant you look at. Well, okay, so what is this, you might ask, first of all, what is this measuring? Well, there, exactly right. So that's the definition. Yeah, exactly right. So singular, but so singular is multiplicity 2 or higher, and somehow multiplicity 3 is supposed to look more singular than multiplicity 2, whatever that means. But so what is this actually measuring? So so here's a little exercise. So there are various ways. So you can kind of see with these double points here, with this double point and this triple point, it's kind of measuring how many branches there are through the origin. But here it's a little more complicated than that. And here, well, this is what's called a normal singularity. This is local. If you took a small ball and removed the origin, it would be locally connected. So you don't have different branches. So this is what's called unibranch. But there's one way of sort of saying what this measures is, the idea is you, let me draw the picture first and then I'll write it down. So let's take this singularity here, and let's look at a little line that meets this singular point. And now let's move just sort of a general line, and let's move this line till it approaches the singular point. Well, if you see what's happening is that there are going to be as we move this line around, there are going to be these two intersection points that converge toward the origin. So provided that the original hypersurface has no repeated factors, this is one way of saying what the multiplicity is. It's how many, you take a general line near the singular point and move the line into the singular point, it's how many intersection points coalesce at 0. So one way to say that more formally is that the multiplicity at 0 of D or of F is a local intersection number. So it's the local intersection number at 0 of D with a general line through the origin, through the singular point.
Over on the left, you wouldn't have any.
But that's because you're too tied. You're not seeing these pictures in C as you're supposed to, right? So remember,
Making you say the things you're not saying.
Right. No, I understand. But I already said that, Dennis. I said we're working with real pictures, but you're supposed to imagine them over C.
The consequence of that is just...
Right. But there's another point that you have to be a little bit careful here, that if you take, there'll be some lines, so if you take a tangent line here, that will have, when you restrict the equation of the curve to this line, that has a triple zero at the origin. So you definitely want to have general lines there, otherwise this doesn't work. So there are going to be some special lines where things are more complicated. Okay, so this is the, let me see, let me just go back to, I'll keep those pictures for one more minute. So this is the one way of saying what this multiplicity is. But now the interesting question is really, when is this the perfect invariant? So this is certainly the first invariant you'd look at, but what you'd really want to ask is, when does this multiplicity, when does this most naive numerical invariant, when does it tell you anything that you might like to know? So let's ask, when does this invariant, the multiplicity at 0 of D or of F, tell you, so this is a vague question, tell you all you might like to know. I'm going to get in, so tell you sort of everything you might like, well, okay. Tell you, well, I mean, it certainly always tells you something, but so everything, yeah, right, everything you might like to know numerically. So when is it kind of the perfect numerical invariant? So this is a little bit vague, but anyway. But let's just look at the pictures and we'll see. So you see, in the case of this nodal, this sort of nodal double point or nodal triple point like this, somehow this invariant is just counting how many branches. So here it's telling you there are 2 branches. Here it's telling you there are 3 branches. Here it's still a kind of a nice thing. But the idea is that in this cusp, this is also a double point, but somehow this is a more complicated singularity than these other double points. That's kind of the theme. And there's a rather clear answer to, the question is a little bit vague, but there's a rather clear answer to it that's going to be important. So the idea is, let's write F, our defining equation. Let's just write out the Taylor series. So we can write out like f sub e, or if it's a polynomial, just write out the polynomial. So plus fe plus 1 plus, where the fi's are the terms that are homogeneous of degree I. So fi is homogeneous of degree I. And then E is the multiplicity. OK, so we're just going to separate out the terms of degree 2, the terms of degree 3, the terms of degree 4, and so on. OK, but now what we can do, this f sub e is a homogeneous polynomial of degree e, degree the multiplicity of our hypersurface. But we can think of it as defining a hypersurface in projective space of 1 dimension down. So the definition, this is certainly the official notation for curves, but anyway, I'm going to use this notation. Not sure this is completely standard in higher dimensions, but it's. So we'll say that f has an ordinary e-fold point, ordinary point of multiplicity ordinary e-fold point, an ordinary singular point of multiplicity E, if what? So what we do is, since f sub E is homogeneous, we can look at its zeros, and we can think of this as a hypersurface in Pn minus 1. So this is actually the projectivized tangent space at 0 to Cn. So this defines some hypersurface in projective space of dimension 1 down. And what we will ask is that this hypersurface is a smooth hypersurface in projective space of degree E. So this is what's called, this f sub E equals 0 is what's called the tangent cone to the hypersurface. But in any event, it's some hypersurface in projective space. And what our definition of an ordinary singularity is that this hypersurface defined by the lowest degree term of f that appears is as nice as it could possibly be. So for example, if we take this nodal curve here, so then we've got w squared minus z squared, that's already homogeneous. So in P1, it just defines 2 points. Here, again, it's homogeneous. In P1, it just defines 3 points. So what this is somehow saying, and here it just defines a conic in the plane. So what this is saying in some vague, not precise sense, but what it's saying is that somehow to the lowest order that appears, this hypersurface looks like the singularity looks somehow like a cone over a smooth hypersurface of dimension 1 less. On the other hand, what's happening here with this cusp is that we're just looking at w squared equals 0. So that's just 1 point, but somehow with multiplicity 2. So here this is not really looking like a cone over something nice in 1 dimension down. So this condition is somehow saying that to the first lowest order that we can see, that this singularity should just look like a cone. This is not precise, but in sort of, it's not analytically a cone over the thing, but that somehow to the lowest order term that appears, it's a cone over something smooth 1 dimension down. And then the general yoga, right. And if E is 1, so it's smooth, then of course this is just the tangent space. So this is the higher order, the best, this is the sort of best thing you can do, closest to the tangent space for a singular thing. And so the yoga here, again, this is not a precise statement, but it certainly, as you'll see during the day, this really governs the whole picture. The yoga is that if x has an ordinary singularity, if our divisor D or our hypersurface has an ordinary singularity, in this sense, at 0, then this multiplicity controls any numerical question you might ask. So then the multiplicity at 0 of D controls the local geometry, at least from the numerical sense. You can't I'm not claiming that you can read off the actual analytic type, but it controls any numerical question you might ask about the local geometry. Well, you'll see during the day. So in other words, you'll see in a few minutes, any reasonable question that just is going to have a numerical answer, if it has an ordinary singularity, you'll see in a few minutes, has an ordinary singularity, it's just going to be governed by the singularity.
That projective variety, are those numerical invariants?
Well, sure, because they're hypersurfaces of a given degree. So a smooth hypersurface of a given.
What about the multiplicity?
Well, this is are you asking x, the singular thing? No,
When you say the multiplicity, you mean that number?
Yeah, the E is the multiplicity. So I'm just saying, this is a little bit vague, I admit, but just give me a few minutes, you'll see. So the point is that we're trying to find numerical invariant. Let me sort of, we're trying to find numerical invariants of singularities. And what I'm claiming is that if you have an ordinary point of multiplicity E, E is the only interesting numerical invariant. So that's not a theorem, but it's a yoga, it's a principle. So for this picture here, the only interesting invariant is going to be the multiplicity. But where the multiplicity isn't kind of as decisive as if you have a non-ordinary singularity, then it's not really, then the multiplicity is kind of the first thing you'd ask, but there's sort of more interesting invariants you can define. But let me just say that to continue the yoga, for non-ordinary singularities, the multiplicity carries less information. So this carries less information. So exactly what we want to do today, what I want to do for the rest of this talk and what the other talks are going to do, is to kind of define and study some invariants that sort of give more numerical information about the singularity in the non-ordinary case. So we want to sort of say the intuition is that this cusp is more singular than this node, but somehow they both have multiplicity too. So we want to find a more subtle invariant that sort of recognizes this as somehow being more singular than that. Okay. Okay, so that's the... And so what is the invariant that we're going to look at, and it's going to be the kind of the star of the show for today. And this is the one, of course, in characteristic P, there's no problem really in defining the multiplicity. That's not a... But so the interesting invariant that's come up over the last, I don't know, 30, 40 years, it's arisen simultaneously in complex geometry and singularity theory and algebraic geometry and arithmetic. And it's what's called the complex, well, it has various different names. So it's what's called the complex singularity exponent, or in algebraic geometry, it's called the log canonical threshold exponent. And this is the main thing I want to talk about today. So this is the log, which in algebraic geometry called the log canonical threshold. Okay. So again, we want to sort of find a more interesting way to measure how dramatic a singularity is. And we're going to do this by considerations of integrability. So again, we consider this hypersurface F. It's a local question, so it's either a polynomial or a convergent power series. And now let's fix some constant C. And then what we can do is we're going to consider the function. So we're going to look at basically the so phi, which way do I want to do it? C of f. So this is going to be the function. What I want to do is I want to look at 1 divided by the modulus of f to the 2c. So this is a nice smooth function that takes, well, c minus the x equals 0 to the reals. And of course, what's happening is it's well, if it's low, let me write it. If I'm working locally, it's just locally defined in any event. So c minus d, so in a neighborhood. And the point is, of course, that what's happening when f is 0, this is blowing up. But now the idea, the sort of intuition is that, well, let me go back here. So the intuition is that we can try to measure how serious the singularities of f are by asking how quickly does this blow up near f equals 0. And one way to measure that is by asking when is this function integrable. So the point now is that if c is very small, so although this is blowing up, it's blowing up relatively slowly, and so this will still be integrable function near 0. So then phi is locally, phi c of f will be locally integrable near 0. On the other hand, if c is very large, then it can't possibly be integrable. So then phi c of f will not be integrable because it will not locally integrable near 0. So the game we're going to play is we're going to start with this f. We're going to let c start with c very small. Then this function is going up, but it's still a finite amount of volume under the graph. And then as we increase c, at a certain point, we lose integrability. And that threshold value of c is what's going to be called the complex singularity exponent, or the log canonical threshold. So this is going to be the star of the show today. OK, so here's the definition. there was maybe the first introduced probably by Varshenko or the Arnold school. So C0 of f, which in algebraic geometry might be called the log canonical threshold of f or of d, is we're just going to take the supremum over all these c's where this function is integrable, locally integrable. So this is some real number, and this is the star of the show today. OK, so the first thing we should do.
What's the date of that?
Well, it's again, I think the Arnold is in the 70s, but I think in the 60s, I'm going to say later on. This, of course, this is one of these things that came up many places. So it was, I think the first case it came up, which I'm going to talk about later, is a theorem of Ragusa, who used it but didn't define it. So anyway, it's a slightly clouded. As anything like this, it's one of these things that once enough people bring it up, then you go back and you figure out that other people have done it. Yeah, so this is the start of the show. Now, it's a slightly confusing thing here, which is this behaves like a kind of like a reciprocal of a multiplicity. So note that slightly confusing, but small c naught corresponds to a big singularity. Because, see, what's happening, the intuition is that if f is very singular, then the bottom will vanish a lot. So c is going to have to be very small in order for this to be integrable. So this kind of behaves like a reciprocal of a multiplicity. So when you're looking at this invariant, if somebody tells you they've got a hypersurface with a very small complex singularity exponent, that means it's a very singular hypersurface. So it's just keep in mind that it's behaving in that sense. Small c naught means a big singularity. And again, I'm not going to talk much about this, and I think Brewer will talk about much more general thing, but you can do the same thing for ideals. So if you have an ideal A, which is generated by some polynomials here, you would study the integrability of the function. You'd study the integrability of the functions phi ca. What you would do is you would take the sum of the moduli squared. Let's see, I hope, do I, maybe I want just to see there. In any event, it's, basically you're studying the sum of the moduli squared of the generators. So again, it's, and then same story. So you get a threshold for an ideal. But I'm going to just take the case of a single polynomial. OK, well, let's do some examples, right? So that's what, of course, we should do. And so we kind of convince ourselves that this is kind of a reasonable thing. OK, so let's start with a polynomial in one variable. So of course, in order for this to make some sense, we've got to understand what happens just with the polynomial z. So it's a little exercise that in one variable z, if we look at the modulus of z to the 2c, this is locally integrable if and only if c is less than 1. So this is going to be the thing that enables us to do all the computations. So this is just the famous, when is 1 over x squared plus y squared, what power of that is integrable? OK. So if that's obvious to you, then you're a real. OK. So that's what happens in one variable. So there's certainly one case we can, just by separation of variables, by Fubini's theorem, we can certainly analyze pretty simply. So supposing we have, we just take a polynomial that's a monomial. So let's just look at z1 to the a1 times z2 to the a2 times zn to the an. So that's some polynomial in n variables. And so when is this going to be integrable? Well, we're just going to separate variables. So each of the terms has to be locally integrable. So if you work this out, you'll see that this is just the minimum of the reciprocal of the AIs. OK, so this is what happens for a single monomial. So for example, if we take our old friend, the node, then the complex singularity exponent is just 1, because this is basically just x squared y squared, z1 squared z1 z2 is what I want to say. So this thing has complex singularity exponent 1. And the point is, as soon as we get into a situation where our defining equation is just monomial, we're happy. Then we just can compute it. So now let's go back to everybody's famous example and compute this for Cusp. So this is kind of fun. OK, so now let's do the Cusp.
This is going to be interesting in finite characteristics.
Yeah, so that's what's interesting. This is going to be computable by yeah, this is the point of the workshop, right? Or something. OK. So let's take our old friend w squared minus, right. So that's the point. I mean, right. So this is the interesting invariant, and it's not obvious that this should be computable f-wise, but something close is. OK, so this is our old friend, the Cusp. And this is again a double point, but it's supposed to be a worse double point, a worse singularity. So we're supposed to, so we need to study the integrals, the integrability. So what we need to do is w squared minus z cubed to the 2c. So we need to ask ourselves, when is that integrable? OK, so what, of course, we're going to do is we're going to make a clever change of variables. So we're going to make the change of variables. OK, so what's our change of variables? So we'll introduce new variables u and v. So z will be u v squared, and w will be u v cubed. I hope I have these right. Yeah, so this looks good. So let's change variables and see where we get. OK. So what happens to our integrand? So what happens to w squared minus z cubed? Well, w squared minus z cubed, if we change variables, let's see, we get u squared v to the 6 minus u squared u cubed v to the 6. And what's coming, this is u squared v to the 6 times 1 minus u. Now we're going to be interested in the question of when is the reciprocal of this thing integrable. So 1 minus u doesn't vanish at the origin, so we're going to ignore the 1 minus u. So the important thing here is that this basically just looks like u squared v to the 6. So at least after ignoring this factor that doesn't vanish at the origin, we've made everything monomial. So this is good. But now, of course, we also want to check what's happening when we, if we're going to study the integral, we better figure out how the volume form changes. So if you take the Jacobian of this map, you'll see that the volume form in u and v, pulls the volume form in z and w, pulls back to modulus u squared times modulus v to the 8th times d vol.
The variables you're pulling back.
Yeah, but it's
Invertible change of
no, it's not an OK. I'm pulling back.
Be a problem. We'll have to do it.
Right.
It only has to be invertible away from a set of measure 0.
Right. I mean, this is a birational map. I'm
Not worried about
right.
that.
OK, OK, I'm introducing new variables. I'm pulling back. Right.
Yeah.
Right. OK. And so what I get in v and w is the zw volume form pulls back to modulus u squared modulus v8. OK. OK, so maybe I should say introduce new variables. OK. So now let's see what happens. What does this integral look like? So my integral, the original integral I look like is d vol of in z and w over modulus, which I never remember which way to do it. So z, I think it's w, which way am I doing it? W squared. I always think of these as x's and y's. OK, so it's like this, to c. So this is less than infinity, and I'll put if and only if in quotes here, so maybe Dennis can see where I'm, tell everybody where I'm cheating. So if I pull this back, what's happening? So let's see. So this thing here, I think, is going to pull back to, so what I'm going to, so let me write this as d vol u and v. So how is this thing going to pull back? So this thing is going to pull, I'm ignoring this factor here. So this thing will pull back to modulus of u to the 4c modulus of v to the 12c. So let me put that here. But I'm not finished. I'm going to write a little bit more times the modulus of v to the 12c. But then I have this change of variables for the volume form. And so I'm going to put this 2 as a minus 2 in the denominator here. So I get 4c minus 2 and 12c minus 8. And so this is what I'm getting. So when I pull this back, I get this thing here. Now, Dennis will tell you that this is, I'm cheating a little bit because this isn't a proper change of coordinates. So in my uv coordinates, maybe something's happening at infinity, but that's not an issue here.
In that statement. That statement is not cheating.
It's not cheating? OK, then I'll. OK. Well, you'll see what's happening in a minute. OK, so I need to figure out when this is finite. But this is a monomial situation. We know how to do this. So what do we need? We need 4c minus 2 is less than 2. And we need, what do we need? We need 12c minus 8 is less than 2. So this says that c should be less than 1. But this is the magic one. This says that c should be less than 10/12, which is the famous 5/6. So whenever you go to a talk on this subject, 5/6 is where the serious stuff begins. You're always supposed to think of 5/6. OK, so now we have to take the supremum of all these. So this is a smaller number than this. So what this means is that the complex singularity, or the exponent of this thing, is 5/6. What?
Taking the female, not the supreme.
Well, whatever. I mean,
Smallest one.
OK, so C0 of this thing in any event is 5/6. OK. And this is obviously less than 1. So you see what's happened. Remember that small C0 means big singularity. So what this means is that this means that it's recognizing that this thing is more singular. These are both, it's recognizing the cusp is more singular than the ordinary double point, because we're getting a smaller value of this thing here. So it's already, you can see that it's kind of already potentially an interesting invariant. And so here's an example. If you're good at integrals, you can do this. Or actually, Demi has a way of actually computing it with. OK, so well, too late. So let me tell you one general computation. These things are very hard to compute, of course, in general. But in general, if you take, for example, a Fermat type hypersurface, so z1 to the e1 plus zn to the en, where the e's are some integers, then what you find is that this is equal to the minimum of 1 and the summation of the reciprocals of the e's. So when we do z squared plus w cubed, we have 1/2 plus 1/3, which is 5/6. And you see, in general, if, for example, we took the e's, if we took e1 to be bigger, let me do it this way, e1 to be less than or equal to e2 less than or equal to en, then the multiplicity is just governed, the multiplicity would just be e1. So all of these things have multiplicity e1, but the higher e's have a contribution to this. So it's picking up subtle higher order information. OK, now I think I've demonstrated very clearly that algebraic geometry should kind of stay away from doing integrals in public, right? I mean, no good comes of that. Well, OK, but there's another way. This isn't how an algebraic geometer would actually do the computation. So there's another way you can kind of, there's another.
That these will always be rational numbers.
Well, I don't think it's true, but
You kind of suggested, right?
that's coming up. That's coming up. But why does it suggest that there
50 years ago, that the Loyas-Wavich exponents.
Well, OK.
One of the ways.
Give me a minute. And what?
This DMI thing that you mentioned is another way of blowing up is to use polar coordinates.
Yeah, he does it in polar coordinates. Yeah.
So that's another way of magnifying the singularity. And then you know that you have all these integers in the polynomial expansion. So strongly
Should come out
expect that it's
rational.
rational.
Yeah, we'll see in a second it's rational. That's going to be the first serious. Okay. So what is it? But so there's another way of doing this, and Dennis says it will show. This is really a computation, I think, of Varshenko, that it will show that this is always. I mean, it's certainly not obvious from the definition that it's rational because it's some supremum of weird real numbers. But you can actually interpret this thing in terms of the sort of some combinatorial data. And so what is going on here? What is it that allowed us, to the extent that we were able to do it at all, to maybe so make substitution, I think I better say.
It is called a change of variables in integration.
Well, no, but that's not, I mean, this is for mathematicians.
So there's going to be a discussion. They can hack out what kind of a. Okay. So of course, what happened, what made this thing doable, is that you make this, you write z as some you introduce new variables u and v, and that has the effect of somehow up to this term that doesn't vanish at the origin, that has the effect of making everything monomial. And by the first computation we did, once everything is monomial, you can just read it off the exponents. And the fact, I mean, what Hironaka's theorem on resolution of singularities basically says is that you can always find new variables.
Sentence again, but
once I've made everything monomial, as we did here, then I can read everything off just because I know how to compute this thing for monomials.
sure. No, then the next sentence.
Right. So the fact is, what Hironaka's theorem on resolution of singularities says is that there's always something like this, whatever it is, that monomializes things.
Oh, really?
Well, that's one way of thinking about it, yeah. So let me state Hironaka's theorem, and I mean, yeah, locally. So let's consider as before, so D in X. So X will be Cn, or I can make it any smooth manifold, or smooth, let's say, algebraic variety. So X could be any smooth algebraic variety. And we'll say that D is locally or globally defined by f equals 0. So f is a polynomial, or maybe locally it's given by a holomorphic function, something like this. So and so we want to find new variables that somehow, when you sort of write out the equation for f in new variables up to these terms that don't vanish, everything becomes monomial. So one way of saying this, so what Hironaka's the theorem on resolution of singularities says, Hironaka, says that there exists, well, the buzzword is a log resolution, but that's what is more classically called an embedded resolution of any hypersurface. So what does that mean? Okay. So in other words, what that means is we can cook up a new variety x prime that maps properly to x. So in other words, there exists a proper morphism u from x prime to x. So this is going to be a proper birational map. And x prime is supposed to be non-singular, so that's good. And what's important is that if I take this hypersurface D and I pull it back, then what I get is what's called a divisor with normal crossing support. So there'll be some coefficients, but it looks locally like just the coordinate, some number of coordinate axes. So
X is the ambient space?
Yeah, so X is Cn, or if you want, it's just, I don't really care what it is. It's just it's wherever D is living. Right, and so what I want to say is that when I pull back my D, I get something that is smooth. But I actually want to say a little bit more than that, because when we did the computation, we wanted to know not only that the equation of D is locally monomial, but also that when I do this change of variables, the volume form, the difference of the volume forms is also locally monomial. So what we ask is that what we ask is if we pull back D, where are we here? Yeah, so the condition is that if we pull back D and we throw in and, well, let me write it as a plus. It just means both of these things are happening. And I take the determinant, the Jacobian determinant. So the determinant of so this is the hypersurface defined, it's the Jacobian of this map. So this is, again, some hypersurface, and I take the corresponding divisor. So these things together should be, is supported on a normal crossing divisor, has simple normal crossing support. So this is just all I'm really saying here. It's various buzzwords, but what I'm really saying here is that when we sort of write everything out in local coordinates, what we're saying is that when we pull back the defining equation and we pull back when we look at the Jacobian of the transformation here, everything up to terms that don't vanish, everything should be just monomials. And, well, since we're integrating, it's not surprising. This gadget here has a special name. Let me just, some notation. It's called the relative canonical divisor, because it's telling us how the holomorphic volume forms differ. So let me just introduce this. Det du is the divisor of this thing. Well, this is called the relative.
Off because in following it, piecemeal, I mean, X up there is Cn.
Yeah.
Here you're kind of referring to X possibly singular.
No. What I'm doing, let me do the standard example, and you'll see. Let me do an example, and if you're still confused, then you can attack. So
X is really Cn there.
X is Cn, yeah.
X prime is still non-singular.
X prime is still non-singular, but what's important is I'm desingularizing the D.
Pull back D, and then D has what property? I mean, I know
It's supported on its.
but what's the formula? I know the picture. What's the formula you're saying? I don't know.
Well, I'm saying it has normal crossing support. So a divisor.
So you wrote something. I'm trying to understand how you wrote expresses that.
The set of points that lie on D is given by a monomial equation.
In local coordinates.
Yeah.
That's the formula.
Let me do that. Let me show. Let's go through the standard example that everybody does, and then you'll see. So we start with the cusp.
So analytically, exchange coordinates defined by the linear equations.
Well, we're getting into this question of what.
Because you just say in the picture, normal crossing, it's smooth.
Yeah, so but it's
Linear.
it's what I did. We're getting into the same fight with.
Position.
No.
We're getting into the same fight. So this has ZW coordinates and this has UV coordinates. I mean, this is what I was doing before. I was started with C2 with equations for ZW. Then I introduced these new coordinates,
Right.
and when I pull everything back.
Just say the picture, normal crossings, but this formula that you wrote has a different interpretation because it gives some multiplicities or something.
Yeah, that's why I say it has normal crossing support. It's monomial. It's given locally by the linear coordinates, but it's monomials in those, so they have some coordinates, some coefficients that you work out.
Right.
So let's do the standard example. So I start here, and I'm gonna blow up. So I start by at each point in C2 I can just do these things by compositions of blow-ups at points. So I'm going to start by blowing up this point. So when I blow up this point, I get an exceptional divisor that I'll call E1. And then if I look at the inverse, actually let me draw this dotted. So my curve, my D will be dotted. Maybe that's better. So this is my D. So when I pull back D, what I'm going to get, if you do the equations, I'm going to get a curve. It's going to be smooth, but it's going to be D pulls back, this cuspidal curve pulls back to a parabola that's tangent to E1. So as soon as I blow up the point and I look at the I take the inverse image of this thing away from the origin and close it up, I get something smooth. But now, the relevant parts of the picture are not intersecting transversely, so I'm not done yet. Okay, so now I'm going to do it again. So I'm going to blow up this point, and then I introduce, and I'm going to do this thing that you already do. I'm going to introduce a new exceptional divisor, E2, and E1 is going to be the sort of image of the old. I'm using the same notation for this E1 and its image there. And when I do this now, the pullback of my curve looks like that. It's a third smooth curve, and they're meeting at a point. And now I have to blow up one more time, so I get E1, E2, I get a new exceptional divisor, so now I'm blowing up here. And then the inverse image of my curve is this thing here. And now I'm happy. So now I've done 3 blow-ups of points. Wait, this is E3. I've done 3 blow-ups of points, and everything in sight is supported on divisors that are meeting transversely.
Above, can you write them on this geometric figure?
Well, yeah, so this is D. And so we can work it out. So if I pull back, let's work it out. So I was going to make this an exercise. If I pull back D, what's happening? So D has a double point. So when I blow up the origin, I'm getting twice E1. So D prime will be this final curve here. I pull back, I get twice E1. Now this thing has a triple point, because I have twice E1 plus D. So E2 will appear with multiplicity 3. And then I have multiplicity 1. 1 plus 2 plus 3 is 6, plus 6 E3. So when I pull it back, this is how my equation is. And plus this D prime, which is harmless. This D prime was the thing that was 1 minus U, or 1 minus V. And where did this funny coordinates come from? The U and V coordinates, or the sort of coordinates here, I forget which is which. But U and V were just the coordinates here. So one of them is defining E3, one of them defining E2, and you just write down what you get, and that's where this change of coordinates come from. And you don't see the D prime anymore because it's not passing through here. The D prime kind of completely disappears from the picture. So the only thing that's interesting, and then you can work out, of course, how the coordinate changes work. I mean, how the change of variables are.
D has been absolved of its sins, and sins are elsewhere.
That's right, exactly, that's right. And so that's a mysterious thing, is that the combinatorics of this resolution carry all sorts of interesting information about, let's see, I'm a little bit behind on time here. Okay.
So the singular point gets replaced by a whole bunch of points, right? So how do you know around where you have to compute the...
Well, yeah, I mean, that's what I was saying before. There are various changes of coordinates you need to make.
So you can just choose any of them?
Yeah, but this is the one that governs the computation.
Oh, okay.
As we'll see. Okay, so...
like local to global, you meant a global thing.
Yeah.
Out of a local thing.
Okay, so let's write, let's see how this works. So let's write, so I'm going back to the general situation. In general, I can write mu upper star of D is a summation Ri EI, and where the EIs are these sort of whatever these funny divisors are, and K, this relative canonical bundle, is a summation BI EI. And now if you work it out, so now we see the point is now we can work out what the integrability condition is. We can work out what the integrability condition is in terms of these combinatorial data. So what is it that we need to do? So we need to compute the volume d vol and x over f to the 2c. So that's what this is finite if and only if when we pull back to x prime, we get something finite. So this is, say, d volume x prime over pullback of f to the 2c. But now I need to multiply. When I multiply, I have to, the volume form on x pulls back times the determinant of du to modulus squared. So this is how the volume form changes. And if you work everything out, what you'll see, right, and if you work everything out, what you'll see is that this is equivalent to, so at this point, you see everything is monomial, so the only thing that's going to depend are these coefficients here. And if you work out what this is saying that the order vanishing along EI of, so what I have to do is this thing is appearing positively, so kx prime over x, those are the b's, minus c times the pullback of d. So all these coefficients should be bigger than -1 for all I. So that's our computation from before. And this just says, so now you see the point is that everything's expressed in terms of these, coefficients. And so this is just saying that bi minus CRI is bigger than minus 1 for all I. And so when we take the, whatever it is, so the C naught of D, we just have to arrange for these things to be satisfied for all I. So what we see is that C naught of D is the minimum over all I of bi plus 1 over Ri. And in particular, it's always a rational number. So this is basically, I think, Varshenko's computation. So in the exercise I more or less did, I wanted to leave this as an exercise. You should recompute the cusp. So now you can just read it off the combinatorics. So especially, and so we get the Varshenko's theorem that this is actually a rational number. So it's really just governed by the combinatorics of a resolution. It's also not totally apparent from the definition that this expression is independent of the resolution. But we're saying that it must be because I've expressed it.
You have the picture, though, from the resolution. You have the actual picture of what's going on.
Yeah, right. But the problem, I mean,
Depend on
there are lots of.
It doesn't either, so the number wouldn't either.
No, but there are lots of different resolutions, and it's hard in general to compare the RIs for the one and the E's. I mean, there's no correspondence between the E's of one and E's of another. I mean, for curves in the plane there is, but they're in higher dimension.
Given one picture, though, don't you have this the geometric structure of the singularity?
Yeah, once you know it's given, anyway, once you know it's given as an integrability, I've defined it intrinsically. But if I define it, I mean, algebraic geometers would take this as the definition.
Oh, I see.
And then it's not obvious that it's independent of the resolution, but you can show that directly. And then maybe I'll mention just one proposition here. Just there's a lot of interesting things you can say about this, and I was going to that we have 1 over. So let me do the. There are some inequalities on this thing, so that the complex singularity of f, exponent of f, is always less. This is elementary. It's always less than the minimum of 1 and the number of variables over the order of vanishing. And what's a little bit more interesting is that it's always bigger than or equal 1 over the order of vanishing of f. This is elementary from the algebra geometric definition, because you just blow up the origin. And moreover, if 0 is an ordinary singularity, then C0, it's just equal to this thing here. So this is what I was trying to say before. It's just the minimum of 1 and n over the order of vanishing of f. So if you have this sort of situation where the tangent cone is nice, then this funny invariant is just computed from the multiplicity. So again, what I'm saying is that in this ordinary case, any of these subtle invariants are just read off of the multiplicity. But what's interesting in general is if you have a more complicated singularity, there's some inequalities, but you don't compute these integrability things just by knowing the order vanishing. Okay, so now let's see. We've got a decision to make. Kevin and Mircea, how important is it to talk about multiplier ideals?
For me, I can do it without, and then you can introduce them.
Okay, I will probably come to that. But the interesting thing about this, I'll do it at the very end, or maybe I'll go 2 minutes over, and the organizers can kill me. What? Yeah, exactly. So one of the interesting things about this invariant is it turns out that this funny invariant controls all sorts of very delicate information about a singularity. So I want to mention the first place this came up was a arithmetic problem that was solved by Ogusa. So this has to do with counting numbers of solutions to an integer polynomial. So okay, so let's consider, I'll just do it in 2 dimensions. So let's consider a polynomial f of zw, but now I want it to have integer coefficients. And I'm going to fix some prime number p. And Dennis, this is a different prime number p than it's coming. This p is independent, is different p. So this is still characteristic 0, as you'll see. Okay. And now we want to, what we can do is we want to, so if we have an integer polynomial, we can look at solutions of this equation mod p. Right? We can plug in integers for z and w, we get an integer answer, and we can look at its solutions mod p or mod p squared, and so on. And so we're going to define, let n sub m.
You're counting integer solutions mod p, or you're
Yeah.
counting solutions mod p?
Well, what else can you count mod? I mean,
No, which is
no, I see. I'm counting the solution. Let me write it down, and then you'll see. So I want to look at the number of pairs x, y in z mod p to the m's. Well, let me just say, so number of pairs x, y. So x and y are integers. So the f of x and y is congruent to 0 modulo p to the m. So I want to look at solutions to a polynomial modulo high powers of a prime. And so I'm thinking of x and y as integers here. And then I'm really thinking of them as integers mod p to the m. So I should really be thinking of this, if you like, x and y are elements in z mod p to the m squared. So this is some finite. Right. So this is some number. And so it's how many solutions does this equation have mod p squared and p to the m, and that depends on m. And so what I want to understand is the asymptotics of this thing with m, or what Gusen want to understand is the asymptotics of this thing in m. So the question is, how does this? So how does nm grow with m? And for those of you who are keeping score, see, this is somehow really a p-adic thing. This is not the, the Weil conjectures, which ask for a number of solutions in a different, as you look at bigger and bigger finite fields. But that's not what this is. This is a much more elementary thing. This is kind of some p-adic thing. So it's still characteristic 0. But anyway, this is OK. And so again, I'm going to be a little bit vague here. But how many pairs x, y are there? So we have the number of possibilities for just x, y is p to the 2m. So this is the number of pairs x, y before we impose any equation. I mean, this is how many things there are here. So we might expect. You'll see what I'm doing. We might expect that nm. So the dominant term should be p to the 2m. But then when we have the equation, we're going to be losing solutions. So I want to expecting that the number so that it's vaguely like this. So I just mean kind of vaguely like this. So b is beta of f. So we're kind of guessing that the number of solutions should be of this form. So f imposes a certain number of conditions, and we'll measure these conditions by this beta. And so now we want to ask ourselves, what does this beta look like? OK, well, let's do some examples. OK, so let's take an ordinary double point. So we'll take f is zw. So this is our old friend like this. And let's count the number of solutions to this, roughly. So what we want to do is we want to, so if we're given integers x and y, so we're asking how many solutions are there to the equation. So we want to know when does p to the m divide x times y, right? This is to say that x times y is congruent to 0 mod p to the m. And as we know, this is the same thing as saying that these m factors of p have to be distributed between the x and the y. So this happens if and only if we have a certain number of factors of p dividing x and a certain number of factors of p dividing y, and k plus l, well, let's say for some k plus l equaling m. Some k plus l equaling m. So this is how many. There's some double counting here, but I'm not going to worry about that. OK, now how many solutions are there? So let's fix k and l. Let me go to a new board. So let's fix k and l. So let's fix k and l. And well, k with k plus l equal m. Now, how many solutions are there? So x has to be divisible by p to the k, and there, p to the m, so how many possibilities are there for x? There are p to the m minus k. That's how many things that are left to choose once I know that x has k factors of p. So there are p to the m minus k possibilities for x. Because I'm thinking of, x, let's say, as an integer between 1 and p to the m. And then similarly, if p to the l divides y, there are p to the l minus k possibilities for y. M minus L, yeah, thanks. So how many, and there's a little bit of overcounting here, but in any event, so nm is approximately what? So m plus 1, that's how many choices there are like that. And then I get p to the, p to the m plus 2m plus k plus l, so that's p to the m, right? Because k plus l is m. And I ignore this term here. So this is basically like p to the m, which is p to the m times 2 minus 1. So here, my beta of this thing is 1. This is just a picture of a node. OK, so let's do the cusp. Let's see what happens if we do a cusp. OK, so let's take f of zw equals w squared minus z cubed, and let's count the number of solutions to this. OK, well, let's assume for simplicity that m is 6 times something else. So assume for simplicity that m is 6 times some other integer, I don't know, k. That makes the computations easier. So I'm not going to claim to write down necessarily all the solutions, but I'll write down a lot of solutions, and then I'll assert with some conviction that this is the dominant number. So how can I, so I want to find a solution. So I want a solution to the equation y squared minus x cubed is congruent to 0 mod p to the 6k. So I'm looking for integer solutions to this. So the easiest way to get this is to make both terms congruent to 0 mod p to the 6k. So I can take y to be, I can take this to be p to the 3k times some y bar. And then if I do this, of course, y squared is congruent to 0 mod p to the m. And I can take x to be p to the 2k times x bar. And so these give me, so then in fact, y squared minus, well, it's congruent to x cubed is congruent to 0 mod p to the m. So if I can just get solutions by just forcing each of the two terms to vanish. Now, how many solutions am I producing like this? Well, the number of solutions is what? So again, so the number of possibilities for x, well, let's do y. For y, so again, I need to just choose the y bar. And so the number of possibilities for y is, for y bar is p to the 3k. And the number of possibilities for x bar is p to the 4k. Because all told, I'm working, means 6k is m. So how many choices do I have altogether? So the total number, so number of possibilities of choices here is what? Is p to the 7k. But that's equal to what? That's equal to p to the 7, remember m was 6k. And then I want to write this as, how do I want to write this? I want to write this as p to the m times 2 minus, so I want to write 7, 6, and so of course that's 2 minus 5, 6. OK, so now, so here, and these are most of the solutions. So here now of course, the game is clear what's happening. So here, the number of solutions, the thing that's governing the number of solutions is the famous 5/6. And so this is Agus's theorem. So what Agus's theorem says is that the pattern that you're seeing here is true in general. So, well, yeah, no, I just want to do it. It is a higher dimensional analog, but it's, yeah, but that's how you have to redefine things a little bit. So let me just state the theorem here. So I want to assume, so this is not the most general form. I want to assume that I have a f polynomial in z and w, and I want to assume, which unfortunately was not satisfied by my first example, but no matter, that it stays irreducible in z times w. So it should be as an analytic function. So it's analytically unibranch, and it should have an isolated singularity at 0 at the origin. And then what we want to say is that this beta naught is exactly this complex singularity exponent. So then the right way to say this is what I want to do is I want to take the mth root of n sub m. So this has the effect of getting rid of these factors like n plus 1, these little multiplicative factors. And I want to take the lim sup of this. And then the theorem is that this is actually p to the 2 minus c naught of f. So in other words, this beta of f is c naught of f. So in fact, this funny integrability exponent in fact governs these arithmetic questions. And the basic picture is that it's going to govern the basic kind of what?
It's not funny for us.
Okay. But yeah, so this was actually, I think this is probably the first place that this C naught appeared. And in fact, it appeared so early that Augusta certainly didn't define it. I mean, I think the definition was from Voroshenko. But the point is that for plane curve, there are these Prizeau exponents, and everything is computable in terms of those. So he didn't really, Augusta certainly didn't talk about, he talked about p-adic integrals, but he certainly didn't look at these kind of complex singularity exponents. So let me just end by saying there's a kind of an interesting, so first of all, you can generalize this to higher dimensions, though it gets a little more subtle. But so this is a nice nice consequence of where this invariant shows up. But there's a kind of an analogous picture that let me just close with this that Mircea found, and this is very important. It's a t-adic analog as opposed to this being kind of p-adic. And this has been very influential. It's saying that defining these invariants in terms of jets and arcs. And this has been very influential because, in fact, you can use this point of view to actually prove most of the basic facts about this thing. So what he did is he found analogous results, analogous picture for what are called arcs or jets. So let me just state in a very, very vague way what this means. So the claim is that this controls. So what you're going to do is instead of, I'm going to look at d of m. So what I want to do is I want to look at d of m is going to be the dimension of this. So what I want to do instead of looking at kind of solutions mod p to the m, I want to look at sort of truncated power series solutions to my polynomials. So I'm going to look at these things here where the xi's are, let's say, power series in T. And I want to look at, and they're going to be kind of truncated, and I want to look at these things so that f of x1 of t through xn of t is congruent to 0 mod t to the n, t to the m, I guess. So I look at power series like this, and I'm really going to, since I'm working mod t to the m, I'm just going to truncate them. So these are just going to be polynomials of degree m minus 1 or less. And so the set of all these things are just governed by, each xi, if it's a polynomial of degree m minus 1 or less, is just given by some finite collection of coefficients. So the set of all things like this is some big affine space. And then I look at the equations in that cut out, the subvariety of that affine space cut out by putting these power series in for f, and I set the linear term 0, set the quadratic term 0, and so on. So I get some complicated bunch of equations. And this is some finite dimensional algebraic variety. It's typically reducible. And then, so for each m, I get some variety in this giant affine space. And you can ask how the dimensions of these things grow with m. And so Mircho's theorem is that somehow these are controlled by this C0 of f in much the same way that the C0 of f controls the solutions mod p to the m.
Over here you were counting, and here you're taking dimension.
Yeah, but this is kind of mod t to the m. That's mod p to the m, right? So, okay, and then there's also this story of multiplier ideals, which I swore I would define, but I will leave that to people. Après moi le déluge, right? So, thank you.